January 15, 1943. Eastern Front near Leningrad. A Tiger I heavy tank, the most feared weapon in the Wehrmacht arsenal, sits immobilized in -30°C cold. The engine runs. The gun works. The crew is ready. But the tank cannot move. Mud and snow have frozen solid between its overlapping road wheels, locking the entire suspension system. The crew has been trying to free the wheels for 6 hours using blowtorches, hammers, and explosives. Nothing works. Mechanics from the battalion workshop arrive with cutting torches. It takes them 48 hours to chip away enough ice to restore mobility. By then, the tactical situation has changed and the Tiger misses the battle it was supposed to fight. This is not an isolated incident. This is the design flaw built into every Tiger tank ever produced. The overlapping road wheel system, intended to distribute the Tiger's massive 54-ton weight and provide smooth ride characteristics, becomes the tank's Achilles heel. Mechanics throughout the Wehrmacht curse this design daily. The wheels overlap in a complex interleaved pattern. 3 wheels on each side overlap each other, meaning you cannot access or repair an inner wheel without removing multiple outer wheels first. A single damaged inner wheel requires removing 18 road wheels, a job that takes a trained crew 10 hours. Under ideal conditions. In combat conditions, it's often impossible. And in winter, when mud freezes between the wheels, the Tiger becomes a 54-ton pillbox. This is the story of history's most feared tank, and the fatal engineering mistake that crippled it. The Tiger I tank enters production in August 1942. As Germany's answer to Soviet heavy tanks. Designed by Henschel and sewn under engineer Erwin Adders, the Tiger is a monster, 54 tons, armed with the legendary 88mm kilowatt K-36 gun that can destroy any Allied tank at 2,000 meters, protected by 100mm of frontal armor that no Allied tank gun can penetrate. The Tiger's combat record is extraordinary. By war's end, Tigers achieve an average kill ratio of approximately 5.7 to 1 against Allied tanks. In combat, the Tiger is nearly invincible. But the Tiger's designers make a critical engineering choice that haunts the tank throughout its service: the Schachterlaufwerk overlapping road wheel suspension system. The overlapping wheel design stems from sound engineering principles. The Tiger weighs 54 tons, substantially heavier than any previous German tank. The Panzer III weighs 23 tons. The Panzer IV weighs 25 tons. This massive weight requires distributing ground pressure across a larger track surface to prevent the tank from sinking into soft ground. German engineers solved this by using wide 725mm tracks supported by numerous small road wheels arranged in an overlapping pattern. Each side of the Tiger has 24 road wheels, 8 large outer wheels overlapping 16 smaller inner wheels. The overlapping arrangement allows the wheels to share load distribution and provides redundancy if individual wheels are damaged. The system works beautifully in theory. On level roads and firm ground, the Tiger's ride quality is excellent compared to other heavy tanks. But the design creates catastrophic maintenance problems that become apparent almost immediately in field service. First, the overlapping pattern means the wheels are packed closely together with minimal clearance between them. Mud, snow, stones, and debris pack into the spaces between wheels. On the Eastern Front, where roads are primitive and terrain is often muddy, this becomes a constant problem. Second, the wheel arrangement makes maintenance extraordinarily difficult. The wheels are mounted on torsion bar suspension. Each wheel connects to a torsion bar that runs across the tank's hull. To remove an inner wheel, mechanics must first remove multiple outer wheels. Specifically, to access the innermost road wheel on one side requires removing 9 outer wheels, a process requiring specialized tools, experienced mechanics, and approximately 10-12 hours of work. Third, and most catastrophically, the design is vulnerable to cold weather. On the Eastern Front, where temperatures routinely drop to -30 or -40 degrees Celsius in winter, any moisture between the wheels freezes solid overnight. The mud, snow, and slush that accumulates during daytime operations freezes into solid ice, locking the wheels together. German tankers quickly learn that a Tiger that runs perfectly in the evening can be completely immobilized by morning, its wheels frozen solid. The only solutions are time-consuming and dangerous: use blowtorches to melt the ice, risking fire, hammer at the ice with sledgehammers, risking damage to wheels and suspension, or pour fuel between the wheels and ignite it, extremely dangerous. None of these methods work reliably in combat conditions. The problem is compounded by spare parts logistics. Each Tiger has 48 road wheels total, 24 per side. The wheels are large, heavy steel components with rubber rims. They wear out from combat damage, rough terrain, and the simple stress of supporting 54 tons. German logistics doctrine calls for Tigers to carry 2 spare road wheels. But replacing a damaged wheel, especially an inner wheel, requires the lengthy removal process. Units operating Tigers quickly discover they spend more time on wheel maintenance than any other repair task. Mechanics in Tiger battalions develop a bitter saying: the Tiger is the best tank in the world for the first 100 kilometers. After that, it's the best job security program for mechanics. Germany produces 1,347 Tiger I tanks between August 1942 and August 1944. Each tank costs approximately 300,000 Reichsmarks, twice the cost of a Panzer IV. Production is slow because the Tiger is hand-assembled with precision machine components. The overlapping wheel suspension requires exact tolerances. Wheels must overlap precisely without jamming. This slows production and makes the Tiger expensive. By comparison, the Soviet TV-34 costs 1/4 as much, and the Soviet Union produces 57,000 of them during the war. Germany cannot win a war of attrition when each Tiger costs 4 times as much as enemy tanks, takes twice as long to build, and requires 10 times the maintenance hours. But in 1942, German planners believe quality will overcome quantity. The Tiger's combat superiority will compensate for its mechanical complexity. This calculation proves disastrously wrong. Mobilized, inner road wheel damaged, requires removal of 9 outer wheels for repair. Estimated repair time: 18 hours. Tiger 123 immobilized, mud packed between road wheels, has dried to consistency of concrete, wheels will not rotate. Attempting to chip away hardened mud with hammers and chisels. These are the elite first production Tigers operated by specially trained crews, and they're spending more time under repair than in combat. Schwer Panzerabteilung 501, the 2nd Tiger unit, deploys to Tunisia in November 1942. The North African desert presents different challenges. Sand penetrates between the overlapping wheels and acts as an abrasive, wearing down the rubber tire rims. The unit reports that road wheel rubber rims wear out after approximately 800 kilometers. Less than 1/3 the expected lifespan. Worse, the sand packs so tightly between wheels that it must be cleaned out daily to prevent jamming. Crews spend 2-3 hours every evening cleaning sand from between the wheels using compressed air, brushes, and high-pressure water when available. If they skip this maintenance, the tank becomes difficult to steer as wheels jam and bind. The unit's commander, Major Hans-Georg Ludder, reports to Army High Command in December 1942. The overlapping wheel design is completely unsuited to desert operations. We require a simplified wheel arrangement, or daily maintenance requirements will render the Tigers operationally ineffective. The problems escalate catastrophically during winter operations on the Eastern Front. Schwerpanzerabteilung 502, now operating near Leningrad, experiences the full nightmare of frozen wheels in January 1943. The unit's morning readiness reports tell a grim story. January 10, 14 Tigers assigned, 6 operational, 8 immobilized with frozen wheels. January 12, 14 Tigers assigned, 4 operational, 10 immobilized with frozen wheels. January 15, 14 Tigers assigned, 2 operational, 12 immobilized. The pattern becomes clear. As temperatures drop below -20 Celsius, operational readiness collapses. The battalion develops desperate countermeasures. Crews are ordered to run engines continuously overnight to generate heat that might prevent freezing. This consumes massive amounts of fuel. The Tiger's Maybach HL 230 engine burns approximately 500 liters per 100 kilometers. Normally, and idling all night adds another 50 to 80 liters of fuel consumption. German fuel logistics cannot support this. Other units try different solutions. Some crews attempt to cover the wheels with tarps to keep snow out. This proves ineffective. Moisture still accumulates and freezes. Some crews park the Tigers over fires built on the ground, hoping rising heat will prevent freezing. This occasionally works, but risks setting the tank on fire if fuel leaks. The most extreme measure involves crews sleeping beside their tanks and waking every 2 hours to move the tank forward and backward several meters, preventing ice from solidifying. This exhausts crews and is impossible during combat operations. By February 1943, German armored commanders are sending urgent reports to Army High Command. The Tigers' overlapping wheels are repairing. This damage in the field requires removing the damaged wheels, which means removing all the overlapping wheels above them, repairing or replacing the damaged components, then reassembling everything. Under combat conditions, this is nearly impossible. The unit's war diary records numerous incidents where Tigers must be abandoned because wheel damage cannot be repaired quickly enough, even though the tank is otherwise functional. But what German tankers and mechanics discover makes this disaster even worse. The overlapping wheels are vulnerable to a specific type of attack that Soviet forces quickly exploit. Soviet anti-tank rifle teams, armed with PTRS 41 14.5 mm anti-tank rifles, discover that while they cannot penetrate a Tiger's armor, they can destroy its road wheels. The PTRS round easily penetrates the steel road wheel rims and shatters the rubber tire. Soviet infantry tactics evolved to specifically target Tiger road wheels. A Tiger with damaged road wheels loses mobility, making it vulnerable to heavier anti-tank weapons or aerial attack. Soviet after-action reports from 1943. 1944. Frequently note, when engaging Tigers, prioritize mobility kills. Target road wheels and tracks. The Tiger becomes helpless when immobilized. The operational impact compounds over time. Tiger battalions in 1943. 1944. Typically report only 50 to 60% operational readiness, with the majority of non-operational tanks suffering from suspension and wheel problems. Compare this to the Panther tank, also introduced in 1943, which has conventional road wheels and achieves 70 to 75% operational readiness after initial teething problems are resolved. The Tiger's mechanical unreliability means that despite its tactical superiority, strategic availability is limited. Units planning operations cannot count on all their Tigers being functional. The Germans' most powerful tank is too often sitting in a repair depot waiting for mechanics to disassemble its wheels. German engineers recognize the problem by mid-1943. The Tiger II, King Tiger, introduced in 1944, switches to a simpler 9-wheel per side design without the extreme overlapping of the Tiger I. But by then, 1,347 Tigers are already in service, all suffering from the wheel design flaw. There are no easy retrofit options. The entire suspension system would need replacement, essentially rebuilding the tank from the hull up. The Tiger I continues in production until August 1944, with the flawed wheel design unchanged. Meanwhile, mechanics continue cursing the overlapping wheels, crews continue spending hours on wheel maintenance, and operational readiness continues suffering. The Tiger remains the most feared tank on any battlefield, when it can actually reach the battlefield. The wheel design's consequences reach catastrophic proportions during Germany's retreats of 1943. 1944. When German forces retreat, damaged or broken down tanks must be either repaired quickly and driven to safety or destroyed to prevent capture. The Tiger's wheel problems make rapid field repair impossible in retreat situations. Unit after action reports from late 1943 reveal the grim pattern. During the retreat from the Dnieper River in October-November 1943, Schwer Panzerabteilung 503 loses 11 of its 14 Tigers. 7 are destroyed by enemy action. 4 are abandoned due to wheel suspension damage that cannot be repaired during the retreat. These 4 Tigers are combat effective in all other respects: guns work, engines work, armor intact. But they cannot move because wheel damage requires 10+ hours of repair time that the retreating units don't have. The statistics of Tiger losses reveal the scope of the problem. German records indicate that of approximately 1,347 Tiger I tanks produced, roughly 40% of total losses are attributed to mechanical breakdown and abandonment rather than enemy fire. Within that 40%, wheel and suspension problems account for approximately 60 to 70% of mechanical abandonments according to post-war analysis. This means roughly 25 to 30% of all Tigers lost, approximately 350 to 400 tanks, are lost specifically due to wheel and suspension failures that render them immobile and unable to retreat. These are not combat losses. These are engineering failures. Germany loses hundreds of its most powerful tanks because they couldn't drive away from the battlefield, not because they were destroyed in combat. The human cost manifests in mechanic casualties and exhaustion. Tiger battalion maintenance companies work around the clock attempting to keep their tanks operational. The average Tiger requires approximately 8 to 10 maintenance man-hours per operational hour, meaning for every hour the Tiger spends in combat, mechanics spend 8-10 hours maintaining it. Approximately 30 to 40% of that maintenance time involves wheel and suspension work. Mechanics work in exposed positions beside broken-down tanks, vulnerable to artillery fire, air attack, and small arms fire. Casualty records for Tiger battalion maintenance personnel show mortality rate 60 to 70% as high as combat crews, extraordinarily high for support troops who theoretically operate behind the lines. The Normandy campaign in summer 1944. Demonstrates the wheel problem's strategic impact. 3 Schwer Panzerabteilungen deploy to Normandy, 101, 102, and 503, with approximately 120 Tigers total. Allied air superiority makes daytime movement suicidal. Tigers must move at night over the bocage terrain, small fields separated by high hedgerows with narrow dirt roads. The bocage tears up Tiger suspensions and wheels. Schwer Panzerabteilung 101's War Diary for June-July. 1944. Records constant wheel problems. On June 15, 8 Tigers operational, 6 down with suspension damage from night march. June 18, 5 Tigers operational, 9 down with wheel and track damage. June 20, 4 Tigers operational, remaining tanks require wheel repairs that cannot be completed under current conditions due to lack of spare parts and continuous air attacks. The spare parts crisis compounds the wheel problem. By 1944. German industrial production is under constant Allied bombing. The Henschel factory at Kassel that produces Tiger road wheels is bombed repeatedly. Spare road wheel production drops from approximately 2,000 wheels per month in 1943 to under 500 per month by mid-1944. Units operating Tigers cannot get replacement wheels. Maintenance officers resort to cannibalizing destroyed or abandoned Tigers for spare wheels. This creates the perverse situation where operational Tigers cannot be repaired because spare parts are unavailable, while destroyed Tigers are stripped for parts. The effectiveness of the Tiger force degrades not through combat attrition, but through inability to maintain the existing tanks. The psychological impact on German tankers is profound. Tiger crews initially take enormous pride in operating the most feared tank in the world. By 1944. That pride is tempered by frustration. Panzer Commander Otto Carius, an ace with 150-plus tank kills in his Tiger, writes in his memoir Tigers in the Mud, the Tiger was mechanically complicated and temperamental. We spent as much time coaxing our Tigers to run as we did fighting in them. The overlapping wheels were a perpetual nightmare, constantly jamming, freezing, or breaking. I've seen combat-experienced crews break down in tears from exhaustion after spending 18 hours trying to repair frozen wheels before a critical battle. This from one of Germany's most successful tank commanders, expressing frustration with his own equipment. The tactical limitations imposed by mechanical unreliability change how Tigers are employed. In 1943. Tigers conduct aggressive offensive operations, exploiting their firepower and armor to spearhead attacks. By 1944. Commanders increasingly employ Tigers in static defensive positions where mechanical problems are less critical. Tigers become essentially mobile pillboxes, moving to defensive positions and remaining there rather than maneuvering actively. This tactical shift reduces the Tiger's effectiveness. The tank's strength is combining firepower, armor, and mobility. When mechanical problems eliminate reliable mobility, the Tiger loses 1/3 of its combat value. Soviet commanders note this shift in intelligence reports from 1944. Tigers are increasingly observed in static positions rather than mobile operations. Enemy appears unable to maintain mechanical reliability necessary for mobile warfare. The Tiger's wheel problem influences post-war tank design fundamentally. Allied technical intelligence teams examining captured Tigers immediately identify the overlapping wheel suspension as a critical weakness. British, American, and Soviet post-war technical reports all conclude that the Tiger's wheel design sacrifices operational reliability for marginal improvements in ride quality and ground pressure distribution. The American Tank Automotive Centers. 1946. Analysis states, the German Tiger's overlapping road wheel design provides excellent ride characteristics and load distribution under ideal conditions. However, maintenance requirements are excessive, cold weather vulnerability is severe, and combat damage to wheels often results in complete mobility loss. This design approach is fundamentally unsuitable for military vehicles requiring high operational readiness. Post-war tank development across all nations moves decisively away from complex overlapping wheel designs. The American M26 Pershing and M46 pattern use conventional six-wheel per side designs with individual road wheel arms. Damaged wheels can be replaced in approximately 30 minutes. The Soviet Tu-54, entering service in 1947, uses 5 large road wheels per side with simple removable designs. The British Centurion uses 6 medium-sized road wheels with straightforward maintenance access. Every major post-war tank design prioritizes maintenance accessibility and field repairability over the theoretical advantages of overlapping wheels. The Tiger's wheel nightmare becomes a cautionary tale taught in military engineering courses. Elegant engineering that fails under operational conditions is worse than simple engineering that works reliably. The operational readiness statistics tell the long-term story. German records indicate that Tiger battalions maintained average operational readiness of 50 to 60% throughout. 1943. 1944. With periods dropping below 40% during winter months or after major operations. Compare this to American M for Sherman battalions that maintained 80 to 90% operational readiness under similar combat conditions, or Soviet Tu-34 battalions that maintained 75 to 85% readiness. The 20 to 30 percentage point difference in operational readiness translates directly to combat power. A Tiger battalion with 45 tanks assigned might have 25 operational at any given time. A Sherman battalion with 45 tanks assigned would have 38 to 40 operational. The Americans can mass 3 operational tanks for every 2 operational Tigers, and since combat outcomes depend on numbers as well as quality, the Americans' reliability advantage often proves decisive. The strategic consequences compound over time. Germany produces 1,347 Tiger I tanks over 2 years at enormous cost in resources, manufacturing capacity, and skilled labor. If those resources had been devoted to producing Panzer IVs, simpler, cheaper, more reliable, Germany could have produced approximately 4,000 to 5,000 additional medium tanks. The German army might have been better served by 4,000 reliable medium tanks than 1,347 unreliable heavy tanks. This calculation ignores the operational readiness factor. Those 4,000 Panzer IVs would maintain 70 to 80% readiness versus the Tiger's 50 to 60%, meaning even more combat power available. Military historian Thomas Jentz concludes, the Tiger program represents a strategic miscalculation. Germany invested enormous resources in small numbers of technologically advanced, but mechanically unreliable tanks when operational conditions required large numbers of simple, reliable tanks. The lessons for modern military procurement are explicit. The U.S. military's current acquisition philosophy emphasizes that new weapons must meet reliability standards before deployment. The F-35 fighter program's troubled development stems partly from reliability problems. But unlike the Tiger, the F-35's reliability issues were addressed before mass production. Modern military doctrine holds that a weapon system that is 80% as effective, but twice as reliable, is operationally superior to a weapon that is 100% effective. But half as reliable. The Tiger represents the cautionary extreme, a weapon so mechanically complicated that its theoretical superiority is negated by its inability to actually reach and remain in combat. German veterans' assessments vary. Some Tiger commanders remain fiercely proud of their tanks and emphasize the Tiger's combat dominance when it functioned properly. Otto Carius maintains that Tiger was the finest tank of the war despite its problems. But German mechanics universally condemn the wheel design. Post-war interviews with Tiger maintenance personnel reveal consistent frustration. Obergefreiter Hans Schneider, a mechanic in Schwer Panzerabteilung 502, states in a 1970 interview, "The Tiger's overlapping wheels were the stupidest design feature I encountered in 6 years of war. We lost tanks and men because of those wheels. I don't care how good the engineering theory was, in practice, it was a disaster. Give me a simple tank I can keep running over a complicated masterpiece that breaks down constantly." This represents the consensus among those who actually maintained the Tigers in field conditions. The Tiger paradox remains: how does history's most feared tank, with combat records showing 5.7 to 1 kill ratios, also suffer from a fundamental design flaw that reduces its operational availability by 30 to 40%? The answer lies in understanding that tactical excellence and strategic effectiveness are different measures. The Tiger was tactically excellent, nearly unbeatable in direct combat. But it was strategically ineffective, too expensive, too rare, too unreliable to influence the war's outcome. Germany needed 10,000 reliable good tanks more than 1,300 unreliable excellent tanks. The overlapping wheel design epitomizes this strategic failure, pursuing engineering perfection that sounds impressive in theory while ignoring the practical realities of mass warfare, logistics, maintenance, and operational reliability. It's a lesson that remains relevant for modern military planners evaluating advanced weapon systems. Remember that Tiger sitting immobilized in -30-degree cold near Leningrad in January 1943. Its overlapping road wheels frozen solid with ice, its crew and mechanics desperately trying to free it using blowtorches and hammers. That scene repeated thousands of times across the Eastern Front, North Africa, Italy, and Normandy throughout 1942. 1945. Every Tiger battalion experienced it. Every Tiger mechanic cursed it. The overlapping wheel design, intended to make the Tiger mechanically superior, instead made it mechanically vulnerable. Those 48 interlocking road wheels, so impressive in engineering drawings, became a maintenance nightmare in field conditions. They froze in winter. They jammed with mud in spring. They packed with sand in desert. They were impossible to repair quickly in combat. They required 10+ hours to access for maintenance. They consumed spare parts that Germany couldn't produce in adequate quantities. And they reduced Germany's most powerful tank to 50 to 60% operational readiness when 80 to 90% was needed. The numbers tell the final story. Germany produces 1,347 Tigers at enormous cost. Approximately 350 to 400 Tigers, 25 to 30% of all Tigers lost, are abandoned due to wheel and suspension failures rather than destroyed in combat. Those tanks cost 105 million to 120 million Reichsmarks collectively, consumed 2,000 to 2,400 months of production time, and required 90 million to 120 million man-hours to manufacture. All wasted because they couldn't drive away from the battlefield when wheels broke down. The Tiger achieves legendary status for its combat performance, killing 5.7 Allied tanks for every Tiger lost in combat. But operational availability tells a darker story. Of those 1,347 Tigers, only 650 to 750 are operationally available on average at any given time. The other half sit in repair depots or are abandoned on battlefields, victims of their own mechanical complexity. Military historian Thomas Jentz calculates that if the resources devoted to Tiger production had instead produced Panzer IVs, Germany would have fielded an additional 4,000 to 5,000 tanks with 75 to 80% operational readiness, providing significantly more combat power than the smaller number of Tigers actually delivered. Today, restored Tigers at the Bovington Tank Museum in England, the Musée des Blindes in France, and the Kubinka Tank Museum in Russia allow visitors to see the overlapping wheel design up close. Museum guides explain the engineering theory behind the design and the practical problems it caused. Military engineering students study the Tiger as a classic case study in over-engineering, when theoretical perfection creates practical failure. The lesson resonates beyond tank design. The Tiger's overlapping wheels represent a fundamental error in military procurement, prioritizing technological sophistication over operational reliability. Germany lost the war partly because it built small numbers of complicated, expensive weapons instead of large numbers of simple, reliable weapons. The Tiger's wheels are the perfect symbol of that strategic mistake, impressively complex, mechanically beautiful, and operationally disastrous. The mechanics who spent 6 years cursing those overlapping wheels understood something German high command never quite grasped: in war, the best weapon is the one that actually works when you need it.